Welcome back, everyone, for a very special episode of Calculus 2. So, this is one of my most favorite lectures. So, we're going to be talking about work again, but this is about problems involving pumping water out of tanks. So, this to me is one of the most cool and interesting of all the lectures in Calculus 2. So, I really love this set of material, and I hope that you'll find this fascinating too. So, first example is an aquarium. So it's 1 foot by 2 foot by 3 feet. And in order to be able to solve this problem, we really need to know which dimension goes where. So here's a picture. So the 1 foot dimension is front to back. The 2 feet is the left to right side. And 3 feet is the side that goes up and down from the floor all the way up to the very top. And we want to find the work that it takes to pump all the water out of the tank. So let me pause for a second and define here what I mean by emptying a tank or pumping all the water out. So this is where the fact that this is a calculus problem comes into play instead of just a regular problem that you could have done in high school physics. From high school physics and from our last video, you probably remember that work is equal to force times distance if, of course, the force isn't changing or anything weird like that. And of course, since the force or everything is changing, that's why we get cool problems, and this is what makes this calculus. So in this example, what we're doing is we're pumping the water out, or we're lifting the water out, and what's changing here is the distance that the water has to move. So the water at the very top of the tank doesn't have very far to go. So what do I mean by pumping the water out? What I really mean is we lift it up to the top of the tank and we throw it over the side. Because if you remember from our discussion last time about work, work only counts when the force is being applied in the same or the opposite direction to the travel of the particle. In other words, lifting the water up to the top of the tank takes work. Once we get it up to the top of the tank, though, I could move the water sideways and dump it over the side, and that doesn't generate any more work. So all I have to do is lift the water up to the top of the tank, and that's as far as I have to worry about. Sliding it over to the side and out of the way doesn't add any more work. So the water at the top of the tank doesn't have very far to go. The water at the bottom of the tank has almost 3 feet to go. So something's changing. We can't just use work is force times distance because the distance is changing now, unlike the problems we had before when we talked about springs. So the most important thing with all these problems is to draw a picture. To draw a picture like I have here on the left, a cross-section picture. Label everything nicely, and as soon as you do that, these become really easy problems to work compared to what they would be if you don't draw the picture. Right? So again, most important thing throughout the rest of this lecture and doing all these homeworks, always, 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 always draw the picture. Label all the coordinates that we're about to go through, and then the problem becomes not too bad. Okay, so the first step after we've drawn our rectangle here over on the side is to decide what we want to use for our coordinates. In other words, what do we want the variable in the problem to mean? So we're going to use x for our variable, even though maybe it would make more sense to use y because we're going up and down, and y make more sense as an up and down variable. But then we've suddenly switched to y's, which feels weird. So we're always going to use x as our variable. And in this case, we're going to let x equal the distance to the top of the tank. Now we'll talk more about exactly what we want to let x equal in the next few minutes. But for now, let x equal the distance to the top of the tank. That's the same as the distance that we have to move the water. So x would start out, right, if it were at the top of the tank, at 0. So I'm always, always, always going to label my coordinates on my picture that I've drawn on the left, which means start with 0, put 0 where it belongs. So 0 is at the top of the tank. When x is at the top of the tank, then it's 0. Okay? Now, what's the bottom of the tank? Well, all the way down to the bottom of the tank, that's 3. You can see from our picture of what the tank looks like. So x floats around, runs back and forth between 0 and 3. That's how we're going to figure out our limits of integration, because our x will run back and forth in the water there between the 0 and the 3. Okay, so if you remember from last time, work is always force times distance, right? So I'm actually going to write it the other way around when I do the integral. You'll see why in just a second. So we need to take the distance that the water has to move, multiply it by the force on the water. So, okay, what water, right? And so far I haven't talked about any water. I've just drawn an X and a little white dotted line. What water are we moving? Well, remember our big idea and all the problems that we're doing, something's changing. In this case, it's the distance we have to move the water. So we can't just use the old formulas by itself. We're going to have to do it on each piece, then add up the pieces. So what are my pieces? Well, the piece here is that little white dotted line of water. So what I'm going to do is imagine taking a little slice of water, right, that will be delta x thick. So that's the up and down dimension there, the thickness of that little dotted white line. So that little dotted white line slab of water, that little piece there, will be delta x thick, right? And it will have a cross section that makes a 1 by 2 rectangle on the top. That's my little piece of water. I'm going to take that little piece of water, I'm going to lift it up to the top, dump it out the side. Then I'll go back and get another little piece of water, lift it up and dump it out the side. So now that I know what I'm moving, what's the distance that that little piece of water has to move? Well, of course, that's just x. That was what we rigged x up to be, right? X is the distance we have to move the water. That's why there's a 0 at the top, right, for x, and a 3 at the bottom. When x is at the bottom, the distance we have to move it would be all the way up to 3. So the distance we move that little piece of water there is x. What's the force on that little piece of water? Well, the force on that little piece of water is just how much it weighs. It's just gravity is what's acting on that little piece of water. So how much does that little piece of water weigh? What's its force? Well, okay, so here's where we get a little interesting. And you notice that there's one line on the slide here that I haven't talked about yet. It's where it says that water weighs 62.4 pounds per cubic feet. What we're given in the problem is a density. So to find the force, we're going to take that density and multiply it by the volume of this little piece of water. Okay, so the density of the um, little piece of water, or density of all water, is 62.4 pounds per cubic foot. The volume of this particular little piece of water that I'm about to lift to the top and throw over the side, well, okay, it's delta x thick, which of course in my integral will become a dx. On one side, it's 1 foot, and on the other side, it's 2 feet. Again, you can look at the picture of the um, of the aquarium that we've drawn over here. It's a 1 foot by 2 foot by delta x foot. So that's our volume. Now, it's worth pausing for a second and go, wait a minute, why did they give me a force, right? What's going on here? And one of the tricks to understanding these kinds of problems and to checking your work is to think about this in terms of units. So what's the units for density? Well, it's pounds per cubic foot, right? You can see that from the thing here, 62.4 pounds per cubic foot. The force should turn out to be pounds. So this is encouraging, right? 62.4 pounds per cubic foot. So if I multiply this 62.4 by some number of cubic foots, then I would end up with pounds, which is my unit of force. So how am I going to get cubic feet? Well, that's what my volume is. Volume is in cubic feet. That's 1 foot times 2 foot times delta x foot, feet, whatever. So those three things, 1, 2, and delta x, those give me my volume. So sometimes people have a tendency to brush over the delta x and not realize that it actually means something, right? But the delta x is really, really very important. In this problem, the dx is part of the dimension of my volume. It's if I didn't have that in there correctly, then I wouldn't get the right force. Now, common mistake people will make though is they'll look at this problem and they'll go, "Oh, it's supposed to be volume. That's 1 foot by 2 foot," and they look at the picture on the right and they'll go, "Oh, it's supposed to be 3 feet." So they'll put in the problem 1, 2, 3. Then they just tack on a dx because they know an integral should have a dx at the end. Of course, that would be wrong because, well, two reasons. One is the volume of this is not 3 feet deep. The whole thing, right? The whole aquarium is 3 feet deep. This little piece of water right there, right, this little dotted white line, that's only delta x deep. Make sense? Right? The other reason why would be wrong is if I put 1 and then 2 and then 3 and then a dx, I would have 1 foot, 2 foot, 3 foot. Delta x is also in foot. That'd give me, well, feet to the fourth power. That's a lot of feet. And that wouldn't give me force when I multiply it by 62.4 pounds per cubic foot. Okay. All right, so all together, I've got my distance, I've got my force. I add those up and let the pieces get smaller and smaller and smaller. That gives me an integral in the limit, and so I'll have the integral from 0 to 3 of all the stuff I just wrote on the screen. Now, how do I know that the limits of integration are 0 and 3? Well, if I look at my picture on the left, the x runs between 0 and 3, so it's super easy to find my limits of integration. If we were just setting up the integral, which is what we'll typically do on exams and such, then there we go, right? Integral's all set up. If we have to work this out and get a number to plug into WebWork or something, the number turns out to be something like 561.6-ish foot-pounds. Okay, notice the foot-pounds because the distance was in feet and that whole force worked out carefully to be in pounds. So the units work here and the units mean something. Okay, well, one of the reasons that I love this lecture and this set of material is because something really cool and interesting happens. It's possible to change the coordinates around and get different looking integrals, but that all give you the same answer. So let me show you what I mean. When we first worked this example, we let x be the distance to the top of the tank. That gave us a nice simple looking integral because, of course, right here, distance was equal to x, and so it was really easy to just put an x there in the box. But we could, right? There's no mathematical reason why we couldn't let x be the distance to the bottom of the tank, right? We just need a variable. Now that means that my 0 and my 3 are backwards now, right? Because the 0 shouldn't be at the top anymore. The 0 should be at the bottom of the tank. And of course, what would be at the top? Well, the 3 would go up there. And there's no reason why we couldn't do our coordinates this way. It'd be sort of like looking in an aquarium while standing on your head. The answer to how much work does it take to pump it out shouldn't matter whether I'm looking at it standing up or whether I'm looking at it standing on my head. It should be the same amount of work either way, although the blood might rush to your head if you were standing on your head too long and pass out. But whatever. The math all works the same way. So if I were to change my coordinates, I can do that. I just need to label my numbers on the side there in that picture with a 0 at the bottom and a 3 at the top. And I take away that x from the distance box and replace it by what it should be now. Okay, so what's my new distance that the water has to move? Well, if I look over here at my picture, the water has to move from x to 3. There's the distance it has to move. So if you think back to the problems we did earlier with washers and shells and this sort of stuff, then when we need to find a distance, it was always the big number minus the small number. That's all it was to it. So which is the bigger number, 3 or x? Well, it's got to be 3 because the x lives between 3 and 0. So the x would be, somewhere smaller than 3. So the big number is the 3, small number is the x. So this distance is just is just 3 minus x. Okay. Now, you may look at this and go, wait a minute, I don't believe this here. This looks too weird. You used to have an x there, and now all of a sudden you've got a 3 minus x, and you're telling me you get the same answer? How in the world is that possible? And you didn't need to change your limits of integration? Why didn't you go 3 at the bottom and 0 at the top? Those are great questions. And the reason that we don't have to change limits of integration is x is still running between 0 and 3. Right? We're just starting pumping water out of the bottom, like you would if you had a siphon pump and you stuck the tube all the way at the bottom and pumped from the bottom. So x is still going between 0 and 3. And when we write our integral, we still put the 0 on the bottom and the 3 on the top in our limits of integration. And so why does putting the 3 minus x in there not change anything? This will make more sense as we see more examples in the next few minutes. But the short answer is these are exactly the same two integrals because you could get from the one on the screen now to the one we had a few minutes ago by using u substitution. If you let u equal 3 minus x and do u substitution to this integral that's on the screen now, you would get the one we had before. Okay? So it's really exactly the same integral. If you don't believe me, then over the next commercial break, then sit down for a second and actually solve out this integral, right? Evaluate this and carefully, maybe I should put parentheses around the 3 minus x, so you realize you'll have to do, be careful when you do the integration. And you'll get 561.6 foot-pounds. I was just kidding about the commercial break. We don't really have a sponsor for this other than the university itself, I guess. So, next up, doing an aquarium is kind of boring, right? I mean, we don't want to just be able to do rectangular stuff. We need something more cool, like a big cylinder. So here's a cylindrical tank. It's 10 feet high, has a radius of 6 feet, and it's full of water. So we want to find out how much work is required to empty it. So always, 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 always draw your picture. Then decide how to do your coordinate system. So like we did the first go round through with the aquarium, I'm going to let x be the distance to the top, or in other words, the distance we have to move the water. That'll make the integral simpler, and it means that I'll put a 0 at the top of my cylindrical tank. 0 goes at the top. Of course, what goes at the bottom? Well, this tank is 10 feet high, so I label the bottom of the tank there as 10. Where's the x? It's sitting there in between, so it looks like my limits of integration are going to be 0 and 10 when I get to that point. Now all I have to do is write out my distance and my force, break this thing up into pieces, multiply all the distance and forces together, add them up, and I should get an integral. The distance is really easy again because that's just x, right? The distance from distance I have to move the water, right, is x. You can see that if I think about it this way, x to 0 is where the water has to go. Which is the bigger number? Well, in this case, it's the x, right? Because x sits between 0 and 10, so the x might be something like 3 or 5 or 7. So x is the big number, 0 is the small number. The distance is x minus 0, or just x. Okay. So next up, how do I figure out the force? Well, just like last time, that'll be density times volume. The density, this is still water. The universe hasn't changed. So this is 62.4 pounds per cubic feet. The volume should be some number of cubic feet. How do I find the volume of this little piece of water? Well, this is a little more complicated than last time because it's not just a rectangle. It's a cylinder that we're pumping water out of. So the thickness of this piece of water will still be delta x, or will become dx when I write it as an integral. But the area, right, won't be a rectangle, be a circle. So the volume of this little piece of water will be pi r squared, whatever the radius is of this little circle, times the thickness dx. In this case, we know that the radius of my cylindrical tank is 6 feet. So pi times 6 feet squared times dx. And again, notice the units work out right because I have pi, which doesn't have any units, 6 feet squared, and then delta x, or dx when it becomes an integral. And that's in feet. So I got 6 feet, delta x feet. That gives me cubic feet. Multiply that by the 62.4 pounds per cubic foot. That leaves me in the big red box with just pounds for my units, which is what force should come out to be. And of course, we saw the x runs between 0 and 10, so we're all good to go. Okay, now let's play this game the other way. Let's put x at the bottom of the tank, which again, this might make perfectly good sense if we're talking about a tank sitting on the ground that's 10 feet high, right? Why should 0 be 10 feet way up in the air, right? Maybe 0 should be ground level. So we put 0 at the bottom, that puts 10 up at the top, x goes in between the two. Now when we start working out our distance and our force, well, the only thing that's really changed here is my distance, and just like last time, big number minus small number, that's 10 minus x is my distance. The force, of course, will be density times volume. That's still 62.4 times pi times the radius of 6 feet squared times my dx. Add all those pieces up, take the limit as my pieces get smaller and smaller and smaller. That becomes an integral from 0 to 10. Again, I know it's 0 to 10 because my limits of integration run from 0 to 10 because the x is running between 0 and 10. Okay, let's play with this problem and make it a little more interesting. Let's say the tank's just half full and there's a 7-foot pipe sticking out the top. So this is a really common way you might see a tank at a oil refinery, or imagine a tank full of gasoline fuel for airplane jet fuel for jet planes, or just water. This is West Texas, so water is extremely precious and important when you're just moving water around. So in all these problems, we're going to be using water so we can keep the same 62.4. But of course, in the homework problems, you'll use lots of other fluids, kerosene and gasoline and milk, lots of different things. There's a table in the book that gives you the density numbers for all those various um, different uh, liquids. And on the exam, you'll probably already know 62.4 because you'll hear me say 62.4 million times as we go through this video. But anything else like milk or kerosene or molasses, the density of any other fluid, I'll give you if you need that on the exam. So here's our tank. It's half full of water and there's a 7-foot pipe sticking out the top. Now I always pause at this point and say, if I tell you that you have a tank and it's half full, I always mean that the liquid is at the bottom half of the tank. Because I actually had a student work this wrong on an exam, or I thought wrong. I'd marked it wrong because they put the water at the top half of the tank, and they argued with me and said, "You didn't tell me which half." So to keep anybody from arguing about this, the water will always be on the bottom half of the tank because we're assuming that we have, like gravity. So the water will always fall to the bottom half of the tank. So let's do this one like we did the first example with the aquarium and the first example with the cylinder. Let's let x be the distance to the top of the tank, which means that 0 goes where? Stop and think about it for a second. That's right. 0 goes at the top of the tank. That means that the bottom of the tank, right, gets a 10 when I label my coordinates. Okay, what else is there? Well, x has to go in there between in the water there where we're moving it around. Okay, well, x is between what and what? Like, where's the water level? Right? Well, the tank's half full, so the water level is at the, in this case, 5-foot mark, halfway between 0 and 10. Right? So we need to label that in the picture for sure, right? This is going to be important because without labeling the 5, we won't know what our limits of integration are. From here, we can see it's really easy. Our limits of integration run between 5 and 10. Okay, now what about this pipe? This pipe is sticking out the top of the tank. So that means that I would have to go, for example, if I'm following along here, if I'm a little piece of water, I'm sitting here at X, I have to go this way. So past 5, past 0, then 7 more feet. So what would this point be all the way up here at the top? Well, that's not going to be 7. I mean, 7's down here, right, near 10. So I'm going to go, X is going to be, 6, 5, 4, 3, 2, 1, 0. Uh-oh, I'm going to have to start using negative numbers. So this top of the pipe here is actually at -7. So if you think about that for a second, this will work when we start calculating our distances, because this is what we need to call that -7 in order to get the distances to work right. So why is it going to do this? Well, again, work is distance times force. What's my distance going to be? Well, I need to go all the way up to the -7 from the x. So just like we did when we were doing washers and shells and stuff, big number minus the small number. What's the bigger number, x or -7? Well, it's x because -7's negative and x is positive. So the x to -7, that distance would be x minus -7. Of course, the two negatives cancel, and so I get x plus 7 is my distance. And if you look at the picture, that's sort of obvious, right? I have to go x to get to the top of the tank, and then 7 more. So x plus 7. My density and my volume are just the same way we did before. The 62.4, the pi times 6 squared dx, because this is the rest of the tank and all still the same. But now what are my limits of integration? Well, x is sitting there between 5 and 10. So 5 and 10 are my limits of integration. Again, always, 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 always draw the picture. If you don't draw the picture, it becomes super easy to get confused about how do I find the distance to the tank? Where's the bottom? What are my limits of integration? But you see, if I draw the picture like I did on the left, all I have to do is just read off the answer, right? Always draw the picture. Then you can just read off the answer. Okay, let's try this another way. In fact, you may be getting bored with the let's try this another way part, but this is one of the reasons why I love this material and why I love teaching this part, because when we used to have student solutions manuals for the textbook that we're using, we'd have students who'd go to the library or go to the bookstore. They could buy a student solutions manual, and it would have some of these problems worked out, mostly the odd questions, and these weren't the questions that got asked in web work. So when we started relying much more heavily on online homework, then students quit buying the solutions manual and eventually quit selling them. But they would work out these problems in the solutions manual, and you would see how it was worked out. The problem was they would do the first problem and they would put x, and let it be the distance to the top of the tank. Then they might work out the next question and let x be the distance to the top of the pipe. Then they might let x be the distance from the bottom of the tank the next time they worked it out. So you try to read these solutions and they work the problem completely differently, of course without a picture, every single time. And so without knowing what's going on, it was just completely bewildering. And what I realized was students, especially in an online class, they'll go on YouTube and look around in other places, Google stuff, maybe go to Khan Academy or wherever, and so they're getting information from lots of different places. And different places will set up these problems different ways. And I realized the only way to make this make sense, even though it means you having to sit through an extra 5 minutes of me droning on about how awesome this stuff is you really have to sort of show everybody all the different ways you could do this, or all the obvious ways you could do this. And then it's like, oh, yeah, 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 okay, I get it. So the next few minutes will be slightly boring, possibly for you, exciting for me because I like teaching this stuff. and, and when we're done, I think you'll really understand why the answer is what it is and all the different ways that you could write down an integral for this problem, all of which are correct. So if I let x be the distance to the top of the pipe, that means 0 goes up where the pipe is, the very top. Instead of -7, it's at 0, which makes maybe more sense, except it makes it harder to figure out what to label the bottom of the tank, right? Down here at the bottom of the tank, what do I call this? Well, it's 10 feet worth of cylinder, 7 feet worth of pipe. So all the way down here at the bottom, that's 17, right? Then, of course, I have my X in there. Right? The top of the tank, what do I call that? Well, 7-foot pipe, and then I reach the top of the tank. So 7 units away from 0, that's 7. That's where the top of the tank is. Okay, what about the water line? Right? What's going on there? That's going to be 7 foot of pipe, then 5 feet of air before I get to the water line. 7 plus 5 gives me 12. So now I'm sitting here with the water line labeled at 12. Makes sense? This is really, really, really important to watch through this, because if you know why I've labeled everything the way that I have, these become super easy to do, or at least as easy as things get in calculus. So I still have distance, I still have force. The distance is as easy as it can get, because how far does the water have to go? Well, in this example, it's from x all the way up here to 0. So big number is x, small number is 0. So x minus 0, which of course is just 0. It's just x. Just x. So the distance is as easy as it can get. The density, well, still 62.4. The volume is still pi times 6 squared dx. Now, what's my limits of integration? Well, it's 12 to 17, because you'll see that the x lives in there between the 12 and the 17. Okay? All right, let's try this again. Let's put 0 at the bottom of the tank. Then, of course, x goes there in the middle. 5 is at the water line. 10 is at the top of the tank, and then 7 more feet above makes 17. This makes perfectly good sense when you label things this way, right? Because if this were actually a tank, sitting on the ground, then you would imagine 0 at ground level and the pipe 17 feet up in the air. Right? The downside to this is, how do I find my distance? Well, big number minus small number, which is the bigger number? 17. So 17 minus x becomes my distance. My density and my volume is the same as it always has been. And my integral now runs between 0 and 5. Right? So that's not too bad. Right? It's super easy to see what my limits of integration are because I just look and see where the x runs between. Okay, last one. Let's let 0 be at the water line. Right? Well, in that case, x would be in here between the water and the 0 and 5. Right? What's at the top of the tank? -5, and the top of the pipe is -12, 7 more units past that. So now what's my distance? Right? Well, it has to be the distance between x and the pipe. What's the big number? Well, it's x, because x is the positive number. So from x to -12, that'd be x minus -12, or x plus 12. Right? And of course, my density, my volume, all that's unchanged. My limits of integration in this case run between 0 and 5. Now, you might notice something that's going on with all these problems. There's this little gold colored box here, right here, where the distance goes. And what's happening in all of these examples is what's in the box has to change between 12 and 17. So let's look at these examples as we go through here, and we'll see what happens. How far does the water actually have to go? In this example, you can see, right, that it has to go from, say, here all the way up to the top of the pipe. How far is that? That's 12 feet. Or the water has to go from the very bottom of the tank, that's at 5, all the way up to the top, that's 17 feet. Everybody see that? So the water actually is going to have to move 12 feet if it's at the top, or as much as 17 feet if it were at the bottom. So what happens in this gold box right here is the numbers run between 12 and 17. You can see here x plus 12, and it runs from 0 plus 12 to 5 plus 12, which is 17. 12 to 17, that's what happens. Let's go back and look at some of our earlier examples, and you can see exactly the same thing happen. So the first time we went through this problem, we had x plus 7 in the little gold box. And our limits of integration were 5 and 10. 5 plus 7 is 12. 10 plus 7 is 17. 12 to 17. That's the distance the water has to travel. Let's check the next one. We used x as our distance. And look, super easy to see limits of integration, 12 to 17 again. Here was 17 minus x for our limits of integration. Well, 0 gives me 17, 5 gives me 12. What's happening each time is that the little gold box is running between 12 and 17. That's why all these integrals are giving us the same answer. What's really going on behind the scenes is U substitution to make it all work out mathematically. And the physics of this is the water has to move somewhere between 12 and 17 feet. All right. Those are cylinders. Let's do a cone. So here's a cone with a diameter of 6 feet. And notice I've changed this. The radius before was 6. Now I've changed my cone so the diameter is 6 feet. That means the radius in the rest of these problems will only be 3. Okay, this one is full of water. We could change this up so that it was, 4 feet deep in water and had a pipe sticking out the top too. But for right now, let's assume that the cone is full of water and we want to empty it out. So it's like a big snow cone full of water. We'll do this the first time by letting x be the distance to the top of the cone. In other words, we put 0 at the top. That means I need to put a 10 at the bottom, and x lives in there between the 0 and the 10. Now, what's my distance and my force? Well, the distance, we know how to do that one by now. 0 and x are the numbers I need to calculate the distance between. X is the big number. So x minus 0, of course, that's just x. The density and the volume get to be a little trickier here, because what makes a cone different than a cylinder is that not only, as I pump the water out, does the distance the water have to move change, but actually at the top, there's more water to move, right? There's a whole lot of water at the top of the cone. At the bottom of the cone, the water has narrowed down to a point. There's very little water at the bottom of this cone. So my density is still 62.4, but the volume, right, of this little white slice of water that I have drawn there would be pi times the radius squared dx. And I'm going to leave that as pi r squared dx for just a second. But the r will change, right? At the very top of the cone, the diameter is 6. That means the radius is 3. So at the very top of my cone, r is 3. By the time I get to the very bottom, it's shrunk down to a point, and r will be 0. So we're going to have to do some geometry to figure out what r is. But at least for now, right, we can leave this in here as an r squared. We'll go back and calculate the r on the next page, and we integrate this from 0 to 10 to get the right answer. So just like last time, setting it up worked like before. We're just going to have to do, well, geometry to figure out the r. Okay, so I really love this part because this is really cool. And one of the things that most textbooks do badly here is they say, you remember how you do similar triangles back in geometry? So if you remember the 10th grade, which you probably don't, then they just do a magic formula and it just gives you the answer. So we're going to do this more slowly and carefully so I can explain to you exactly where this comes from. And I'm going to do it in a geometry way, and I'm also going to show you a trig way of thinking about this that maybe seems like it would make more sense given how far back it's been since you've done geometry for most of you. Here's what I'm going to do. I'm going to draw a line down the middle of this cone there. And I'm going to separate this out to make a big triangle. So I said there's a triangle happening here. So I just draw a line from the center of the circle, it's at the top of the cone, straight down to the point at the bottom. I'll color the part below X there in white so we can see it. And now, one of the reasons why I love doing these sort of animated videos is I get to do this, right? This is cool. In a live class, I'll say ooh, and the whole class will usually go ah, and so imagine sitting where you are that this is impressive. It may not be so impressive in a world full of, Star Wars special effects, but for me, this was pretty cool. So I have this big blue triangle and a little white triangle. And as you remember from high school geometry, or don't remember from high school geometry because that's been a long time ago, these are similar triangles. That means that the angles are all the same. Or to say it more carefully, the angles of the blue triangle match the angles in the white triangle, right? So these are both right triangles. So there is a right angle here and here. This angle is, of course, the same as this angle, and the angle at the bottom is the same angle because they both come from the point down at the bottom. So how long is this side that I've drawn? Well, that was the whole length of the cone. That's just 10. What about the top of the blue triangle? Well, that was the radius up at the top. So that was just 3. On my white triangle, then this side is the distance here, right? That's the distance from, well, between x and 10. So again, big number minus small number. The big number is the 10. So that distance is 10 minus x. And then this side of the white triangle is r. That's what we're after, right? The radius side. Now, as you remember, hopefully, about similar triangles, right? This ratio has to happen. 3 is to 10 as r is to 10 minus x. There's a couple of different ways to think about this. One is to say, oh, it's a similar triangle, blah, 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 and write this down and go. Geometry books in high school will mutter something about the sides being proportional, which means that 3 is to 10, right? The top is to the side there. 3 is to 10 as r is to 10 minus x. You see those match up. Another way to do that is to talk about how one triangle has been multiplied by a scale factor to turn into the other. We're not going to do that. What usually works for calculus students more than anything else, though, is if I point out that both of these fractions are equal to the tangent of theta. Right? What's theta? Theta is the angle here at the bottom of the cone. Because remember, what's the tangent? It's the opposite over the adjacent. Again, there was my 90-degree angle, right? So opposite over adjacent. Well, if I look at this in the big triangle, I get 3 over 10. If I look at it in the white triangle, I get r over 10 minus x. But these are the same angle, so it's the same tangent. So these two fractions have to be the same. Okay? And a lot of times that's easier to remember than trying to do geometry. Because geometry, it's been so long ago, may feel more like, like evil magic or something at this point. So how do I figure out what r is? I have this nice fraction. Let's multiply both sides by 10 minus x, right? Or another way of saying is take the 10 minus x over to the other side. That tells me that r has to be 3/10 times 10 minus x. Now, again, when you're playing with something strange like like dark magic or geometry, then it's a good idea to check your answer here and make sure we didn't do something wrong. So, if I were at the top of this cone where x was 0, what would my radius be? Right? If x is equal to 0 at the very top, then the radius should be 3, right? I'd be looking at the full radius. Okay? So let's check. If I plug 0 into this equation, 10 minus 0 would be 10. The parentheses 10 would cancel with the denominator 10, and sure enough, it leaves me with r equal to 3. On the other hand, by the time x gets to the bottom and become 10, right, x is 10, so my radius is shrunk down to nothing, so I should get r equal to 0 when x is 10. And so I plug 10 into the equation, and sure enough, 10 minus 10 gives me 0, which when I multiply by 3/10 still gives me 0, so that matches. So I feel like, okay, I haven't made a silly mistake with my geometry, we're all good. Okay. Now what we'll do is we'll take that placeholder r squared, we'll throw it away, okay, and we'll slide the pi and the dx apart and move the correct radius down into the integral, and there we go. Finally, at last, we have our integral, which is harder to integrate now, but at least it's correct, right? We have an r, we don't have an r floating around as a placeholder. We have the actual um, expression for the radius of my triangle. So, as I said before, I love these kind of problems. I think these are just really, really cool because you can work this problem several different ways. I'll let you think about different ways you could have put 0 or ways you could have put a pipe at the top or stuff. There's lots of examples of that in the homework. But I really, really like these questions. I think these are really cool, and they make you think about um, what we're really doing here. That we're breaking things up into pieces, adding up the pieces to get an integral for the answer.